All right, so I'm going to talk about quantum phase transition of metals. So the idea here is that we start with the Fermi liquid state that Sohn just described, and then ask, is there some phase transition to some other state, which is also a metal, um, and ask what happens, what kind of other phases you get. And today I'll also say, if there's time, something about the nature of the critical point in some cases. Um, Right. And the important thing in all of this is really keeping track of what's happening to the Fermi surface. So that's really the central actor here. So I mentioned that there were three possible cases. Um, the, the first two are sometimes in the category called Hertz-Miller's theory because of their early work. And there are two cases within that, both of which involve some kind of broken symmetry. But in one case, the change in the Fermi surface is just some small deformation. So this would be the case, for example, in a ferromagnet. So a ferromagnet, both up and down spin have the same Fermi surface. And then once there's a phase transition, one of the Fermi surfaces shrinks and the other one grows a little bit beyond the critical point. Case two would be in an antiferromagnet. So in an antiferromagnet, on the lattice scale, the order parameter is some large wave vector like pi pi. And if this connects 2 points in the Fermi surface, then at these hotspots, you have a strong coupling between the order parameter and the Fermi surface. And so you get a theory where the low energy theory is right near the hotspots. So finally, today I will talk about the third case more, where this is the more exotic case, where there's no broken symmetry, but because of some change in the entanglement structure of the wave function, you're going to get two different phases. So all right, so that's case three. And the one case that I discussed last time is in the Kondo lattice, where you can essentially prove the existence of at least two phases. So you imagine the Kondo lattice has conduction electrons coupled to some localized F spins, which are represented by S. And then the F spins have interactions between themselves called J sub H. So now you imagine a situation where these two subsystems are decoupled. So the conduction electrons are just free electrons. JK is zero. And this Hamiltonian is chosen so that this system has a spin liquid. So then you get a state of matter, which is schematically illustrated here, where the F spins form some kind of spin liquid with themselves, whereas the conduction electrons are free to move around. And then I presented an argument that this state of matter is stable for small jk for just about any spin liquid. And so now in the new phase, at finite jk, you have a violation of the Luttinger relation because the Fermi surface is also stable under perturbation in jk, so has size p, whereas the density of electrons per unit cell is 1 plus p. Okay, and the way you get out of this phase is by a quantum phase transition to a conventional Fermi liquid, which obeys the required Luttinger relation. And that happens by the condensation of an anion. So this is one of the simplest examples of an anion condensation that I think Caroline will say much more about tomorrow. Here, this is the case for a gapless system. And so here you have a boson, which is the hybridization of the conduction electron and the spin-on, whatever the spin-on may be. And now, of course, this spin-on has to be a fermion for phi to be a boson. And so this transition sort of requires this spin liquid to have fermionic spin-ons, although there could be cases where they don't. And then the nature of the transition is still is more difficult. Anyway, so once this boson condenses, then you can write down some mean field Hamiltonian for the conduction electrons and for the hybridization between the conduction electron and the F spins mediated by this condensate. And then you could also take the J sub H term and decouple it by Hubbard-Stranovic transformation, and that gives you the hopping of these spin-ons. Anyway, now once you're in this phase, because phi has condensed, the Fs effectively become electrons once you fix the phase of phi. And so this is just a simple electron, two-band electronic Hamiltonian, and this will then obey, since it's free fermions at this point, the usual Luttinger theorem with density 1 plus p. Okay, so any questions on that quick review? All right, so now the thing I want to do now, which I started at the end of my last lecture, is can this happen in a single band model, like the Hubbard model? Now for the Kondo lattice, as you can see, it was really very simple, because the way you violate the Luttinger theorem is by localizing some of the fermions into a spin liquid. Now, for the Kondo lattice, it's very clear. You just take the F electrons and put them in a spin liquid, and that's what's going to happen. But if you have a single band system and you want to violate the Luttinger theorem, meaning that the Fermi surface does not have density 1 plus p, size 1 plus p, then you've got to localize the electrons, but the question is which ones? All right, so there's various ways of talking about it, which I indicated last time, which involve complicated processes of binding holons, spin-ons, and so on. But I'll present a method due to Yahui Zhang, which I believe really clarifies a very clean way to do it, which at least even also sets up a gauge theory for the phase transition between the two phases. So the idea is the following. So the main trick we're using is to add some trivial insulator. You can think of this as just a Hamiltonian formulation of the Hubbard-Strudnovich transformation, because when you do a Hubbard-Strudnovich transformation, you decouple something and you get some bosonic field, and formally, of course, you haven't added any degrees of freedom, but if you set it up in a Hamiltonian form, you want to do it in a way so that the additional degrees of freedom have a trivial ground state. In this case, it's a bilayer antiferromagnet. So they just form these rung singlets, and there's a gap about a J perp, and we think of J perp as being large. So this new Hamiltonian is an expanded Hilbert space, but the extra states, which are the excited states, are all above some energy about a J perp, and so perhaps they don't influence the low energy structure. Well, at this point, they don't, because there's no coupling between them. But we're going to induce a coupling by doing a canonical transformation, U, and get a new Hamiltonian, which is the ancilla Hamiltonian, which is illustrated here. Now we have a coupling J Kondo between the extra degrees of ancillas and the physical electrons. So that's the price we pay. We have an extra coupling. But what we gain, at least formally, is you can, these electrons here become free. So you have free electrons coupled to an antiferromagnet now. So here's a more precise way of thinking about it. In fact, it's easier to go backwards. Suppose I start with this model of free electrons coupled by JK to this bilayer antiferromagnet. Then I can do a canonical transformation order by order in JK, where these are projected onto their singlets. And when you do that, you can show, and this is what we've shown, you get a Hubbard model for C, and this is the precise value of U to order JK squared, JK cubed, and you can keep going. Of course, at next order, you'll start getting intersite couplings and so on. But it's really possible to work this out. All right, so now we have this Hamiltonian, and we'd like to understand its structure. So first of all, if J perp is really large, then these spins will form singlets, and you're done. I mean, okay, then you just have free fermions, and you have a Fermi liquid. Everything is boring. So, so where we can rigorously derive all this, there's not much more to say. You just get back to where you started. On the other hand, we know that for the single site Kondo problem, so if we just had one spin here, coupled to conduction electrons, all the enormous amount of work on the Kondo problem says that the Kondo coupling is relevant. So if you start out with a small antiferromagnetic coupling, it flows off to infinity. And Wilson et al. Have a famous RMP article where they actually compute that complete flow. And the whole Kondo physics is about the flow of JK to infinity and the formation of Kondo singlets and so on. So here, we're going to assume, although we don't have just single spins, that for a while we can follow this flow, at least for a while. So we can entertain the idea that JK becomes larger. So we ask what happens when JK becomes larger. So I can draw this phase diagram now. So we are going to now, I'm going to argue that when JK becomes larger, you will get this, this new phase of matter with the violation of the Luttinger theorem. I should emphasize, notice the change in orientation. For this Kondo lattice, large JK gave you the Fermi liquid. But now for this model, because it's a single band model, large JK gives you the more exotic phase. All right, so what happens at large JK? Well, first of all, as I already said, at small JK, these spins form singlets, and this field phi, which I'll introduce in a minute, has zero expectation value. This is the analog of the same boson or anion condensation. So what happens at large JK? Well, so let's imagine JK is infinity. Well, JK is infinity, I can forget about the bottom layer. And the top two layers is exactly the Kondo lattice I just talked about. So for large JK, that we know that for this Kondo lattice, you'll get the condensation of this anion, this phi, and you'll get the heavy Fermi liquid state, which has, in the case of the Kondo lattice, a large Fermi surface. A large simply means you count up the density of all the electrons. Well, in this case, the density of the top layer is 1 plus p. The density of the bottom layer is 1. So the total density is 2 plus p, but everything is modulo 2 because you can have filled bands and remove them. So it's p. So in fact, it's small Fermi surface. So in this case, the heavy Fermi liquid state has a small Fermi surface. And then what about the bottom layer? Well, it better form a spin liquid, and let's assume it does. Forms your favorite spin liquid. You can put any spin liquid you want here. And then you have this FL star state, which has violated the Luttinger theorem. And Oshikawa tells us if you violate the Luttinger theorem, as you did by the top two layers, then there must be some fractionalized excitations. And sure enough, there they are. Okay? So that's what I mean by saying this is Oshikawa for dummies. All you're doing is just keep applying the same trick that we know worked extremely well for the Kondo lattice. I mean, the original theory I presented for the Kondo lattice, has been tested in experiments, even numerically. It's really a beautiful theory of the heavy Fermi liquid phase, which has been very successful. So here, we're just taking that same trick and applying it to these ancillas and getting a more exotic phase because you've got the spin liquid at the bottom. All right. So now we can write down some effective Hamiltonian. It's exactly the same set of tricks we did for the Kondo lattice. Basically, you have essentially the same Hamiltonian that I had for the Kondo lattice. We assume there's some, in mean field theory, that the bottom layer is some spin liquid and it's just decoupled. Now these T1 and phi are your variational parameters that you can vary to get the best possible state for the moving electrons in the small Fermi surface. And you can also choose different spin liquids and then you get a trial wave function. So what will the trial wave function look like for the physical electron? So here's a wave function which we propose as a replacement for what's called the vanilla wave function for the cuprates. So in the vanilla wave function, you just took one Fermi surface and you did a Gutzwiller projection and just had projected all W occupied side. So what we do is something different. We first include the ancillas. So we've expanded out the degrees of freedom. And then you take the top two layers and you form a Slater determinant of the conduction electrons and the F electrons. And you can choose any dispersion you want. So the dispersion of the C and the F and the hybridization are your variational parameters. You pick your favorite spin liquid for S2. So now this is a wave function on the expanded Hilbert space. And then finally, you do a projection. But now the projection is you project out these extra degrees of freedom onto singlets. Okay, so you're measuring these spins and make sure that every pair is a singlet. All right, so, and that gives you then a wave function, a trial wave function for this doped spin liquid, which has a small Fermi surface of electrons. I mean, there's lots of wave functions for holons and other exotic objects, but what we need, and what experiments seem to tell us, is a wave function for electrons. So Yahoo has a nice way of putting this, where you form some Fermi surface. So that's free fermions. It's the world's simplest wave function, but very hard to describe by tensor networks or something like that. But then you take your very complicated spin liquid wave function here, which is whatever exotic features you want. And when you do the projection, it's like a measurement. And you measure, by doing a measurement, you're teleporting the entanglement of the spin liquid into the Fermi surface. So that's what the whole idea is. You use the Kondo lattice theory, and you just build up everything with it. Anyway, okay, so now let me show you some numerical results that are just about to appear. So what these works have been doing is try to fit these experiments at the moment. So these are the cold atom experiments of fermions in the Hubbard model. These are the results of the Munich group. At that time, they were at some relatively high temperature. And I think now there's new experiments at significantly lower temperatures and more precision. Okay, we'll have to catch up with that. So at these higher temperatures, they see what looks like some kind of phase transition in two metals. At high doping, you have a Fermi liquid. At low doping, they have what they call a polaronic metal. So in this language, their language, the polaron is just a bound state of a spin-on and a holon. And there's a finite density of them. So what they measure are these multi-point correlation functions shown here as a function of doping. So they find where the holes are, and every time there's a hole, you measure the 2-point spin correlation there. So this is really like a 3-point correlation function. And as you see, there's a dramatic difference, even at these high temperatures, between what happens at low doping in the region where you don't have magnetic order to over here where you get the Fermi liquid. Anyway, so I'm going to showing you here results soon to appear by Henry Shackleton and Shiwei Zhang, and there's a parallel paper by a few other people. This is comparing, here's the wave function they work with, where they have a variational parameter for phi. And the hard part here is doing the projection onto the singlet subspace. In fact, there's a certain sign problem there, but Henry's come up with some very clever ways of conquering it, or at least over some reasonable system size. And then you determine phi by computing the energy. You start with the Hubbard model. You take a Hubbard model and you minimize the energy of the Hubbard model to determine phi as a variational parameter. And it seems to work very well. I don't want to go into all the details here. Not that I'm very familiar with them, but it's really very encouraging how well this wave function works. So it's a good starting point for describing. And the phi itself, as you determine it variationally, vanishes at some point. And so when phi vanishes, then you just get a free Fermi, large Fermi surface here. Okay. Now, we've also done a lot of work on using this to compare to the cuprates. Let me just quickly flash one thing anyway. So for example, this is the Fermi surface, see the cuprate, this is what we fit with, and then we can plot we can compute the dispersion on the antinodal region, and so on. So I don't want to go into any of that because I want to move to the next part of my talk. But let me just leave it over here. Okay. Yeah, so this is the main result. That's the general idea. I think it's a really powerful idea, and can be applied in many different contexts, and allows you to really give you a way of handling not only the presence of spin liquids, but also the binding of holons and spin-ons into electrons in a very systematic way. Yeah. Well, that's how you could motivate it, yes. But another way to think about it is just in terms of Hubbard-Stratonovich transformation. So you can start with the Hubbard model, and you decouple the U term, and you get a phi squared. In fact, I did that, right? Yes, on Tuesday. You had a theory for the Hubbard model, which is some field phi, which is a vector field, plus phi dot c dagger sigma c, and there was an e to the I k dot r over here. So I had this is an exact rewriting of the Hubbard model. So what is this phi? This phi is really, it's not a spin, it's a rotor variable. It's like a vector field with a singlet ground state and higher excited state. So it carries spin 1, but its Hilbert space has spin 0, spin 1, spin 2, and so on. Phi is an operator that takes you from spin 0 to spin 1. So what we're doing here is we're taking this field phi and writing it in terms of 2 spin-a-halves. So this phi is the paramagnon. So we're really fractionalizing the paramagnon. We're taking the spin fluctuation and writing it in terms of spin-a-half variables. That's what the ancillas are. Each of them is half a paramagnon. And that, so what we're avoiding is fractionalizing the electron, because the electron doesn't want to fractionalize. The electron, T is much bigger than J. So holon and spin-ons have a very strong attractive interaction between them. So you totally avoid that at any step. Yeah.
Fractionalized excitations in the ancilla spin liquid also excitations of the
Absolutely. So we are talking about the Hubbard model. Our Hilbert space is of the Hubbard model. The point is we've added some extra states, but those, initially were decoupled. So, we're still talking about this system here. Oops. This is our system, okay? And in this combined system, there are some excited states, but who cares? They're not excitations of this. Now, when we do the canonical transformation, we are writing the Hubbard model in slightly different terms. Maybe this is look at this picture. In this picture, we start from here, and when we do the canonical transformation, we project all of these spins into a singlet. And so we just left with the Hubbard model. So the other degrees of freedom are just gone. Okay, so the physical electron operator is some linear combination of the C, some composite operator of the C and the S1 and the S2 with just the right quantum numbers. So this is all about just the Hubbard model. We're not doing anything more. We're just analyzing it in a way that allows us to violate the Luttinger theorem in a quite systematic way. Well, that's a question of terminology. That's I think Senthil came up with FL star. So it's a Fermi liquid, yes, because the quasi-particles, so for example, the quasi-particles are electrons, have exactly the electron quantum number. I can apply Landau's, everything Sohn talked about, I can apply to that Fermi surface. But now this system has another set of excitations, which are the spin-ons of this spin liquid. So if I did neutron scattering on the Hubbard model in this phase, I would see two sets of spin excitation. I would see the usual excitations of a Fermi surface, but a small Fermi surface. And I would also see the spin-ons of the spin liquid. Okay, and there's, I think, quite a bit of evidence for such two sectors in the neutron scattering and the cuprates, but nothing quantitative that I can report to you yet.
Spin-ons are all these per domain.
Yeah, the dispersion of the spin-ons will be J, yeah. So they should be there eventually. Well, part of the trouble for numerics, at least, is that you can't really go to zero temperature and do it very precisely. But as we're seeing in the cold atoms, it's not really that much of a problem if you have more precise data from the experiments. Yeah. Yeah, there's some M star. I can't compute it. It could be heavy because of it is a Kondo lattice. So there's an M star here. We know that roughly M star is 1 over J, not 1 over T, and that's something come here. And in fact, the value of phi determines the pseudo gap in the antinodal region. So you can fit it from the data very easily. So that's about 30 MeV. Yeah, so there's a lot of work we've done comparing this theory to photo emission in the cuprates, and well, I want to get off to the next topic. All right, any other questions? Okay, so then I can start my next set of slides. Okay. All right, so I want to now talk about the critical point. And I'll begin by, well, not right away, but I'll summarize what we know about the critical point in the clean case. And as I've already mentioned in my very first lecture, it really simply doesn't agree with the experiments. It has a lot of very serious problems. And then we've been studying, and several other people also, the disordered case, and which has also been studied a while back by many people, especially Thomas Voiter. And all of that is starting to come together now, and we think we're at least to get some coherent picture of the strange metal, but we'll see. All right, so I'll begin with another so the critical point will be a non-Fermi liquid of some type. It cannot as yet be described by the kind of theory that Sohn's talking about. So we need so I want to begin by a simple solvable model of many fermions that does not have any quasi-particle excitations. And that's the SYK model. So if I just show you in pictures, you imagine you have some set of orbitals on which you occupy some electrons, and these can now move around. And you just put one restriction that they never move on their own, but they always move in pairs. So there's some matrix elements for electrons on sites 11 and 12 to go to site 5 and 14, and so on. So every such quartet of sites has some complex number associated with it. And this is the Hamiltonian you want to solve. And the remarkable fact is that you can solve it in the large N limit with just one assumption. The assumption is that these numbers are independent random numbers. Okay, and that's the SYK model. So here it is written out in Hamiltonian form. You have this two-body interaction, U alpha, beta, gamma, delta. Curiously, actually exactly this Hamiltonian was written down by nuclear physicists in the 80s. But they did some numerics, and that's about it. This is something I discovered much later. And these are just fermions, and there's some, in this version of it, there's a conserved charge. These are not Majoranas, because I want to apply them to systems which have a conserved charge. So that's Q. and the charge density is between 0 and 1. So I'm ignoring spin here. All right, so one of the things you notice is this peculiar factor of 1 over n to the 3 halves here. And that's needed to get a regular large n limit where the excitations have energies of order 1. Okay, so, and the total energies of order n. Now, so how does one solve this? So there's various ways of doing it, but the simplest way to solve it is to just do perturbation theory. So if you just, and then average graph by graph. So if you do perturbation theory, you know, at first order, you'll have a graph like this. Sorry, this is the U, and these are the fermions. So, but now if you average this, because the average value of U is 0, this is just 0. Okay, so then you go to next order. So at next order, you will get the following graph. You have a U here, and another U here. Something like this. This is one graph you're going to get, and then you're also going to get, whoops, something like this is, for example, and well, there's a U here and a U here, and another graph like that, say. And you can write on many other graphs at order U squared and so on and so forth. And now you're going to average all this. So now initially, all these indices are independent indices for beta, gamma, delta. Okay, it's conserved in the free particle, so this is still delta. This is gamma. This is beta. Well, and that was that. Okay, that is free at the moment. This could be alpha prime. But when you do the average, because they're uncorrelated, the indices have to match. So if the indices match, then that has to be alpha 2. And now you have to sum over the intermediate indices. There's 3 of them. So that gives you a factor of n cubed. And each interaction has a factor of 1 over n to the 3 half. This has a factor of 1 over n to the 3 halves. And so it's 1. So this graph survives the large n limit. Okay, that's why that was chosen that. But if you look at this graph, you have no such luck. So this is alpha. Well, let's say this is beta, then this will also be beta. This is gamma. This is gamma. Because it's the same line. And this could be delta, say that has to be delta. And this could be alpha prime. All right, so now you see that when you do the average, alpha, alpha prime, beta, delta must equal what's going on here. So alpha and alpha prime could be both equal to gamma. And this, so that would work. This would be alpha. This would be alpha after you do the average. Then it's non-zero. But now you notice this, you have 1 over n cubed 10 to the 3 halves here. You have 1 over n to the 3 halves here. But you only have sum over beta and delta. That gives you n squared. Okay, so the whole thing is down by, it's about a 1 over n. All right, so you can very laboriously look at all possible graphs. And it turns out there's only one set of graphs. This is not the way we originally did it. You can do some path integrals and get the results. But that's the most pedestrian way. It turns out to be, there's only one graph that survives, which is this graph, which I just drew on the top. It's not just one graph, but notice that the G, the intermediate G, is not the bare G, it's the fully renormalized G. So this is sometimes called the melon graph. So it's all melons within melons within melons. You just have to sum all of them. Okay. All right, so this gives you this set of equations. The only thing here, all the Green's function only depend on frequency, so that's since there's no space. So this is just the Dyson equation. You have 2 unknowns, sigma and g. And this is the expression for this graph. Sigma is minus u squared and g squared g. All right. So that looks simple enough, but it's really quite a complicated problem because the Dyson equation is simple in frequency space, whereas the self-energy equation is simple in time space. And then you also have to respect all the analyticity properties of the Green's function. So you have to look at really carefully solutions of this equation and see what you can work out, which respects all of these properties. Okay, so, and you hope to find such a solution for a range of values of Q. The Majorana case is like the square of this problem, and Q is 1/2. All right, so this is what, these are the equations I wrote down in 92. And I thought I'd solve them in a few weeks with the help of Jinwoo, but no, we did made some progress, but we're still learning new things about these equations, especially, so understanding the full singularity structure or something only became possible by the work of Maldacena and Stanford, and in fact, hiding in these equations is some version of quantum gravity in one space and one time dimension. Okay, certainly in 92, couldn't have imagined that. All right, so what is the solution? So this is something we had obtained by 2001, but this is now an applied math problem, of solving these three equations. So I give you Q, and that determines the value of mu, and then you have to solve for G and sigma. So these are fully determined. You can put this on a computer and solve them. And today, that's very rapid, although in those days, computers are not as good. So anyway, so what you can argue, so you make an assumption. You make an assumption, well, first of all, let's look at this a bit more. So the first thing you can ask yourself, is there a solution? Maybe there's no solution. All right. So first thing you ask, is there a solution which has a gap, meaning that there's a finite range of energies over which imaginary part of G is 0? Well, if there's a gap in G, then from this equation, we see that the gap in sigma is 3 times the gap of G, because you just cut this graph, you're creating 3 particles, so you need 3 times the energy to create that. But from this equation, you see that if there's any gap in sigma, if sigma becomes imaginary, then immediately G becomes imaginary. The gap in G and the gap in sigma can't be different because they both become imaginary along the real axis with its I omega is gone at the same time. So the only possibility is gap is infinity or gap is 0. Gap is infinity means there's nothing, but maybe that's the only answer. But the gap is 0, well, there's a gapless solution. So if there's gapless, well, it has to be some power law. So you make an ansatz. So you make an ansatz shown here. This is the solution, but you make an ansatz with some coefficient of tau to some power for positive and negative time, and allowing for the 2 coefficients to be different. Here, the ratio of those we now parameterize in terms of this capital E. Okay, so now you make this ansatz, you plug it in and work it out. And we showed that there is a solution where this exponent is 1/2. So it's clearly in a non-Fermi liquid. In this kind of state, in a Fermi liquid, this is like the local Green's function. It will decay at 1/tau. This doesn't prove that there are no quasi-particles. There could be some other fractionalized particle. But for that, we have to wait a minute to rule that out. And somewhat later, in this paper with George and Parcolet, we also showed that there was a Lettinger theorem. There's no Fermi surface here, but there's still this anomaly effect that's fixing the particle-hole asymmetry. So this tau greater than 0 and tau less than 0 at 0 temperature are just the Green's functions of a particle in a hole. And this epsilon is a measure of the size of the particle-hole asymmetry. And that's exactly what a Fermi wave vector 2 is, right? It's telling you about where the excitation changed from particles to hole in momentum space. There's no momentum space here. But nevertheless, there turns out to be an exact relation given by these two equations between the particle-hole asymmetry as measured by epsilon, which is the analog of the Fermi wave vector, and the charge Q. All right. So that involves actually going through the argument I presented in my first lecture for Luttinger's theorem, applying in this case. And then I mentioned at some point that there's a Luttinger-Ward functional, and the contribution of the Luttinger-Ward functional to the density vanishes. In this problem, it does not vanish. And that's where these relations come from. And these have been numerically checked. Actually, we checked them already in 2001, and they work beautifully. Okay. Sorry, yes? Yeah, I barely know what an anomaly is. I'm just using the word. It's because it smells like a lot of other things. There's no flux piercing argument I can make, but it's definitely tied to when you do the argument, like you're you look at how the action changes to a time-dependent gauge U1 transformation. And when you go through that argument, you find that there's this kind of constraint on the total charge. Yeah, so it's sort of, you're doing a time-dependent gauge transformation, so that, in that sense, like a 't Hooft anomaly. Yeah. Okay, that's the best I can do. Actually, Yingfei has some better answer. He wrote an appendix to one of our papers where he explained this more carefully. So I'll point you to that appendix. Okay. All right. So now what Georges and Parcollet already showed in '99, and now we know how to do much better, is also solve these equations at finite temperature. Small temperature, much smaller than U. And it turns out that there is, quite remarkably for such a random system, for any density, provided the solution exists, there's an emergent conformal symmetry. And as Kitev argued, there's also the action itself has an emergent time reparameterization symmetry. And so using arguments based on that, and also by explicit solution in '99, you can see that, okay, I'm just writing it this way, anticipating what we're going to say later, that basically if you go to finite temperature, all observables scale in the sense that the natural energy scale is only temperature and not U. So there's some scaling function here, which depending on how you define tau, you can compute. And all times have a characteristic scale, which is h bar over kt. Okay, so this is what we call Planckian dynamics today. So that's great because it's very suggestive, because precisely this kind of scaling is seen in numerous experiments. So I mean, that's certainly already in '93. I mean, we couldn't compute this or prove this, but that was very much the motivation for this model. Another feature, which we also discovered in 2001 paper, is somewhat remarkable. It's not, as far as I know, not seen in any other model before, which is this model has a zero temperature entropy. And what I mean by that is precisely this limit, where you send n to infinity first, and then send t to 0, and look at the entropy per particle. That turns out to be non-zero. So that seems to violate the third law of thermodynamics. But the order of limits is really crucial here. This is not the statement, and that's what's remarkable. In all other cases where you had violated the third law of thermodynamics, this happened because of an exponentially large ground state degeneracy. So for example, there's, of course, famous Pauling's ice entropy, which is a purely classical model, which has many different exactly degenerate ground state. And that gives you a zero temperature entropy because the ground state is massively degenerate. That's not what happens here. The ground state is non-degenerate. I mean, maybe it has a degeneracy of 1 or 2, depending on certain symmetry classes. So the way it happens is that the density of low energy states, and here's a numerical plot of the density of states for all these states, is exponentially large down to essentially zero energy. And that's how you get an entropy. That's sufficient to give you a zero temperature entropy without a ground state degeneracy. So this is something new that came out here. I mean, it took us a while to appreciate this phenomenon. But it's really the essence of this model. So now this turned out to be really the key to the connection to black holes, especially extremal black holes, because they have exactly this property that they have a zero temperature entropy. But in the string theory realizations, that entropy is realized by degeneracy. So in all the calculations in string theory with supersymmetric black holes, the entropy is a consequence of a degeneracy of the ground state. Whereas, so now, however, with this, we now understand much more about non-supersymmetric extremal black holes. And they actually behave like this. They have a non-zero entropy, but they do not have a degeneracy. Okay, so this is great for black holes, but it's not great for condensed matter because there's no evidence for anything like this in experiments in any strange metal or anything. So the question, which I have 20 minutes to resolve, can I preserve this property and other properties, but not have this? Of course, this is a very artificial model in zero dimensions. It turns out to be just the ticket for understanding extremal black holes, which I won't talk about. But it needs something more to apply to strange metals. Okay. Right. Okay. So that's all I'm going to say about the SYK model itself. Any questions?
So this is the question.
What?
That you want to keep property 1 without property 2? An open question, or you're going to resolve it?
Oh, we're going to resolve it. We certainly have an example. Is that the solution for the real experiments? You can decide.
Question.
Yeah.
And the experiment, strange metal seems to be explaining in kind of high temperatures.
Yeah.
Why is the model targeting to understand zero temperature?
Well, okay. So here there's only one scale, which is U, and U or J. J is about 2,000 Kelvin, and U is 10,000 Kelvin or something in cuprates. And the experiment we're talking about at most 200 Kelvin. So even what's the high temperature region of the phase diagram is really quite low. And that was also evident in, in this cold atom experiment. They were, that's a heroic experiment. Oh, that was the previous. That cold atom experiment I showed you is a heroic effort to get very, very low temperature. But on the scale of TC, and they're still kind of high. But so here we are, we're assuming that this kind of physics is of some slightly unstable ground state. And so could be visible at low temperatures once you get over that instability. Okay. I have so Kitaev solved this much later, and then he wrote down an expression in Santa Barbara for the entropy. And I looked at it, and I was watching it online. Oh, is that agree with our? I had no idea our result was correct, and I got a different result. So I emailed him. I'm sorry, I have a slightly different result. And then he said, oh no, there was a typo, and he corrected the typo, and it was exactly the same. So big relief. Yes.
Results change when U has a mean.
Well, short answer, but I think you can just, you can just do some Hartree correction and absorb it in the chemical potential. So that's not so hard, I think. I mean, if If it's all to all, no, U on every site, yeah, then you can get certain phase transitions, and we've studied a lot. Yeah, so, but you can get phases like this, but you also get many other things. Yeah. Yeah, if you look up our reviews on modern physics articles, there's whole sections on that kind of thing. All right, but that article, was trying to answer precisely this question. How do you preserve property 1 but not property 2 and get something more reasonable? And we were looking in many different directions, which are summarized in the article. But only towards the end, while that article is being completed, we realized there's a slightly different direction to take, which is what I'm going to describe, which gives you the solution that we think is the right direction. Okay. So first, now let's go back to this type 1, 2, and 3 phase transition in clean metals. And I'm just going to consider type 1 in this case. So then this is the theory I wrote down last time. So you have a Fermi liquid here, and then you have a scalar field, which represents some broken symmetry. Right, done some 5-fold field theory with it. And then you have this coupling G, psi dagger, psi phi. So I think how you wrote down exactly this theory in his discussion in the Gong Show. And so we said, okay, let's try to solve this theory by a self-consistent method where you put extra flavor labels and everything. In particular, you make this G a function of some fictitious flavor label, and then you take the large N limit. So you basically put flavors on all the fermions and the bosons, but the most important term is this one. So you have some local term, G alpha beta gamma, phi alpha, psi dagger beta, psi gamma. But this is translationally invariant, is independent of x. You still have exact translational symmetry. And then, of course, G alpha beta gamma. There's a 1 over n here. Average is 0 to begin with. And then G alpha gamma squared is some G squared. All right, so by exactly the same tricks, you can figure out what this is going to give. But notice here, most importantly, this is in finite dimensions. There's a Fermi surface for psi. There's a dispersion for phi, and so on. Anyway, so you do those same set of tricks, and you end up with this graph. So here you have two Green's functions. G is the Green's function for psi, and D is the Green's function for phi, and sigma is dg. My computer, oh, shit. Sorry, it wasn't connected to the power supply. Okay, it'll take a few minutes then. Okay, sigma is dg, so I can just write on the board and while it comes back up. Oh, well, it'll take a few minutes to charge. Oh, something's happening? No, that's somebody else. I'm gonna have to go back on Zoom, sorry. Okay, so you have this sigma of tau, and x is d of tau, d of x and tau times g of x and tau. And then the self-energy of the boson, which we call pi of x and tau, is something like g squared. Okay, you can sit down and solve these equations. Now, these are much more complicated equations because the self-energy, the Green's function depends on momentum. You have to take a Fourier transform both in space and time. But the self-energy is only a function of frequency. So that simplifies things quite a bit. Anyway, so you can go in and try to solve these equations. And in fact, the equations were already obtained before. In fact, they're in Polchinski's article on Fermi surface coupled to a gauge field. He wasn't motivating it this way. but he showed that essentially these equations have a simple exact solution. And okay, I'm back up. This here. Sorry, I have to start Zoom again. And the solution he obtained, okay, share. All right. Okay, so the solution he obtained was actually had been obtained. So these are the actual equations, and this was the equation that Polchinski, the solution he obtained, and this has been actually already obtained by Patrick Lee in '89. So you get a self-energy, which is omega to the 2/3 power, so that's highly non-Fermi liquid-like. And you get a bosonic propagator, which has this mod omega over Q damping that we know from, that I talked about from the Hertz theory way back when. Okay, so the notes actually go through some detailed calculation where I actually evaluate a lot of these integrals. It's not so simple, but it's the kind of thing, you learn how to do when you're really deep into many-body theory with Fermi surfaces. You get these integrals that you now know, but I'm not going to do it on the board or anything. You can, but all the steps, at least for the simple calculation, are in the notes. What's kind of remarkable is that you can even get the coefficient here exactly, even though these are nonlinear, complicated equations. They have an exact solution, which is in fact more exact than for the SYK model. For the SYK model, there are certain things you can't determine as well. So, and what happens really here is that when you do the integral in the direction orthogonal to the Fermi surface, this n direction that Son also mentioned, that integral can be done exactly, and many of the results are independent of the self-energy. And that's why, for example, this gamma coefficient here can be determined exactly. Anyway, so this is great. This is a very nice looking non-Fermi liquid. The self-energy is omega to the 2/3, so it's very large, meaning that there's no quasi-particle pole. But one very important point, there's still a Fermi surface. That is, if there's a point here where if you take the imaginary part of the self-energy, that vanishes at 0 frequency. And then when E of k changes sign, you get a Fermi surface. So this is a non-Fermi liquid. So the Fermi surface is a much more robust thing than quasi-particles. It's a Fermi surface which is very broad in frequency space, but it's sharp in momentum space. And furthermore, the volume enclosed by the Fermi surface still obeys the Luttinger relation. So the Luttinger relation and the existence of a Fermi surface is still defined. I wrote down this equation a while back. Right. The Fermi surface is defined by the equation G inverse of k, and omega equals 0 equals 0. Well, you could take this Green's function, which is non-Fermi liquid-like because of this very large self-energy at finite frequency, but at 0 frequency, it has a solution. And in fact, the solution does obey the Luttinger theorem. So yeah, so that's another very important fact about non-Fermi liquids. You just can't get rid of the Fermi surface. Except by what I talked about earlier, by forming spin liquids. And if you compute the entropy, you don't get the 0 temperature entropy. In this case, it's T to the 2/3. So it's larger than a Fermi liquid, but it doesn't go to non-zero value as T goes to 0. Okay, so that's exciting. And certainly there was a period when many people thought this was the right direction. We've got the entropy, maybe there's an enhancement of specific heat. Now let's just compute other properties like transport, and everything will eventually fall into space. Well, okay, So let's talk about transport next. So that was looked at already in this paper in 94 by Kim et al. And they computed both the DC conductivity and the optical conductivity. Let me just focus on the optical conductivity, where they found associated with this omega to the minus 2/3 self-energy, omega to the 2/3 self-energy, conductivity that vanished as omega to the minus, had this tail at finite frequencies bigger than temperature of omega to the minus 2/3. Now remember, in a metal, the conductivity, in a perfect metal, is just a delta function. You put in a few impurities, it's a Lorentzian, which decays as omega squared. So there's some very slow decay. And they wrote down these graphs that you have to evaluate, where the wavy line is the boson and the full line is the fermion, and everything they wrote down is correct. And in fact, when we do our large N limit, we get exactly the same graphs that the large N limit tells us we have to evaluate. But this coefficient C turns out to be 0. Okay. You know, if you just how you actually, and also Darius Zhenghan here, evaluated all the integrals that were in this paper and just add the terms up, you get 0. So in fact, this is not, as far as transport is concerned, it's not a strange metal or anything. It's a Fermi, it's actually a perfect metal. You can put in some impurities and then ask what happens. Do you get something bizarre? Something how you looked at, and the answer is no, it's still a very good metal. Okay, so what is this due to? Well, there's various ways of understanding it, but the short way to say it is we're talking about very low energy processes on the Fermi surface. If you have a Fermi surface and then you're getting lots of singular scattering, that's small momenta near the Fermi surface. So the system you're looking at is basically insensitive to what's happening away from the Fermi surface. Now let's take a very simple model where I can solve things exactly, where I only change things away from the Fermi surface. So for example, if I take a quadratically dispersive Fermi gas and couple it to some boson, that theory is actually Galilean invariant. And in a Galilean invariant theory, and this is Cohn's theorem, this is the exact conductivity. It's just a delta function at the cyclotron frequency if you have a magnetic field. So 0 magnetic field, that's 0, and so the real part of sigma is a delta function at 0 frequency. That's the exact result for any Galilean invariant Fermi system, Fermi liquid or not. It simply follows from the conservation laws. Now, the system is not Galilean invariant, so there are certain operators and certain effects that come from the curvature of the Fermi surface and various other things, which actually Hayu has studied in great detail and a much better understanding in some of his recent papers. At best, they give you some positive power of omega over here. So this term here is something that would not be present. This would be completely absent in a Galilean invariant system, but here, because of non-exact Galilean invariance, you get some small corrections. Another interpretation is what's called drag. So, you know, this issue also comes up in what's called the electron phonon problem, which was first looked at by Bloch in the 1930s in a paper that's written in German. He derived what we now call Bloch's law, which is the resistivity of a three-dimensional metal at low temperatures due to electron phonon scattering vanishes as T to the power 5, where he just computed, you know, what's the probability that an electron will scatter off a phonon and put that into Boltzmann's equation. Okay, and then soon after, Piles wrote another paper, which was forgotten, that Bloch is incorrect. And he said that, yes, the electron can scatter over phonon, but because of these are all very low energy, long wavelength processes, eventually the phonon will give the momentum back to the electron, and there will be essentially zero resistance. Now, people did the experiment, everybody agreed, everything agreed with Bloch, so it seems like piles was forgotten. Now, why was Bloch right experimentally, even though his theory was wrong? Well, because two reasons. One, the electron-phonon coupling is weak, and two, there's always impurities. So the impurities will relax the momentum, and so since its electron scatters off a phonon only rarely, in between two scattering events, the phonon has plenty of time to find an impurity and dump its momentum there. So once an electron scatters over a phonon, you can forget that phonon in the electron-phonon problem. So to really see drag in the electron-phonon problem, you have to have a really pure sample. And it's only in recent years that Andy McKinsey has been seeing these effects. Here, however, the electron-boson coupling is so strong. It's not the weakest thing in the problem, it's the strongest thing in the problem. It's so strong that the electron doesn't even exist. In fact, it makes no sense to talk about momentum carried by the electron versus momentum carried by the boson. They're the same thing. They're all in some collective, very strongly interacting soup. So you can only talk about the collective momentum, and that needs something to relax. All right, so after that tirade, I have 5 minutes left. So what is the answer? So we were convinced, we still are, the answer is impurities. You have to think about impurities. There is another effect called Umklapp, but it's hard to see how Umklapp can be operative at low temperatures, and it requires special fine-tuning of the Fermi surface to get appreciable Umklapp. So the most generic phenomenon, since the strange metal behavior is extremely generic, so seen in hundreds of compounds, there should be some very generic effect. And so I'll describe that generic effect. And the beautiful thing is that I talked about 3 different classes, types 1, 2, and 3 of quantum phase transitions. The same theory applies to all 3, essentially. So that's great because the phenomenology is also really robust and universal, experimentally. All right, so what we have to worry about, and this is a recent paper with a few people, I guess. Okay, we're going to take this theory. This is for type 1, but very similar things work for other types, and put in some impurities. All right, so the most common type of impurity, which is what the entire theory of metals is based on, is the potential scattering V of R. So you take some random function V of R, which is spatially 0 in average, and has some delta function correlation. Okay, so this gives you if you take this theory, you get the Drude theory of metals, the oldest theory in solid-state physics, with sigma of omega has this Drude peak and so on and so forth. If you really look at complicated effects of V of R, then you get localization, Anderson localization, and so on. So you're going to assume that here, especially in 2 dimensions, this Anderson localization happens on very long length scales. There's no real evidence for it in the experiments. And so we're going to ignore those localization effects. But much more important is another effect, much more important than electron localization. The other effect, this I've already talked about, is a spatially random mass. Okay, so this thing, what will this do? Well, this tells you that this is some random function delta S. This tells you that this point of the sample has a critical point at S equals 1. This point has a critical point at S equals -2, and so on. So the position of the critical point fluctuates, and we're just going to put in some small fluctuation. And this is, in fact, by far the strongest effect that's present in any sample, really, because nothing is homogeneous. Much more important than the disorder due to V. And these localization and Altshuler-Aronoff corrections, those are really subdominant compared to this. All right, okay, this can we apply the same set of bag of tricks? Let's just average over, put in some flavor labels and solve this. We did try that. Unfortunately, it doesn't work. And the reason it doesn't work is because this perturbation is really way too strong. You have to treat it essentially exactly. And so this is what we've been working on, trying to think of this exactly. All right, so the first attempt, which actually works for a while, is the way you can treat this exactly is by rescaling phi so that this becomes spatially uniform. So if you rescale phi, then this will become spatially uniform, but everything else will become spatially inhomogeneous. But we're going to just keep the most important term, which is spatial inhomogeneity in the Yukawa coupling. All right. So in a sense, you have exactly solved for the random boson mass, but put the problem somewhere else where it doesn't have such a strong effect. And now you can take this theory and apply the usual SYK bag of tricks. You know, I had these, I'm out of time, right? I had these equations earlier for the clean problem, and now you can add the extra terms that come from the V disorder and G disorder, and now you just turn the crank and solve all of this. Okay, so you know, everything is here, it's just a matter of solving these equations, and again, you can actually, so now we have actually numerically solved these equations, at least for the case G is 0 when the self-energies are independent of momentum, but completely, and I'll show you some of the results. But we can also perturbatively look at the effects of G and G prime at the same time. All right, so what do you get? Well, you get, you know, things that got us pretty excited. You get, for example, the self-energy has a where does it go? 1 over tau of omega is linear function of frequency. That's the inelastic scattering. It comes from both G and G prime, and that's what Varma et al. Called a marginal Fermi liquid. So quite generically, you get a marginal Fermi liquid spectrum. And then you put it in conductivity, and this is really the first calculation that you get linear T resistivity in the conductivity because you get this transport time, which is a linear function of frequency or temperature. But notice one very important thing. The linearity here only depends on the random coupling, whereas here it has contribution both from the average and the random coupling. And this is because of exactly this drag effect I talked about. Long wavelength scattering without impurities does not give you linear T resistivity. Okay. All right, I'm pretty much out of time, so let me just flash a few things. So we have computed in this limit numerically the whole phase diagram. This is the resistivity as a function of temperature. As you move away from the critical point, it's linear in T at the critical point, and then linear with quadratic behavior at low temperatures. The optical conduct, so that kind of linear in T many people can get by lots of scattering of some set of low energy excitations. But what's most striking is that the optical conductivity does have kind of a 1 over omega tail, and that also comes out here. So this is the data, this is our calculation, and then you can also compute this tau of omega, and this is the data, which in fact, the data shows the scaling, and in fact, the entropy is T log T from various measurements, and that's exactly what comes out of this model. Anyway, okay. I think I'm pretty much done. So let me just conclude by tell you something about ongoing work, especially by Avishkar Patel. So if you look at an actual phase diagram where you suppress the superconductivity and look really what happened at low temperature, what's much more common is this foot. Okay, so this is the regions which are red is where the resistivity is linear in temperature. Regions which are blue are where the resistivity is T squared. So this is lanthanum, strontium, copper oxide. The dashed line is where the critical temperature is, and you've suppressed it down to 0 by applying a magnetic field. So what you see is you see this quantum critical fan. I mean, there's this fan up here, which is quite similar, you know, to this fan here, where we're only on one side of the transition, though. like this fan here that we get in our theory, where we do just solving these Green's functions. But you see, you get what's called the foot. You get some other extended critical region at very low temperature where this resistance is still linear in temperature. And I think there are several proposals on what this is due to, and they all involve Griffith's effects, as they're called. And in our language, what we say is that in this region here where we have the fan, you have essentially this kind of SYK physics of self-averaging extended bosons and extended fermions. And what happens at low temperatures is not that the fermions localize, but the bosons localize. So the bosonic collective excitation become very local. And we have various evidence from numerics, and Avishkar and Peter have another paper coming from quantum Monte Carlo where they see all of this physics. So I think I'll just stop there.
What do you know about the nature of the excitations in the Yukawa SYK model?
I mean, if you're really talking about the actual Yukawa SYK model in 2 dimensions with spatial disorder, well, that's the very low temperature limit, where you have localized bosons, like they're sort of like 2-level systems interacting with some disordered fermions. But if you're talking about up here, let's say 100 Kelvin and above, well, that's I've given you the Green's functions for that, which agree with a lot of data. These are the results. I mean, this is what the Green's function is. That's what the transport is, and it's a marginal Fermi liquid as far as the self energy is concerned. But it just turned out that the transport properties of a marginal Fermi liquid had not been done properly before, and that's what we've shown how to do it correctly. And then it gives you, yeah. I mean, first of all, we didn't tune it we didn't postulate a marginal Fermi liquid. It's what this comes out very generically from our calculation.
Right.
So the many-body negative states, roughly speaking, you can say is e to the entropy. So that you can get by Laplace transform of this entropy is T log T. So it vanishes. It doesn't go to some constant. It gives you T log T. So there is no zero temperature entropy. There's some, I think this gives you, I don't know, e to the square root of T with some log corrections, square root of e. Yeah, something like that.
Quasi-particles versus strange fractionalized quasi-particles that are created by the electron operator.
Well, the self energies, yeah, we could only analyze this in this particular approximation. There are no quasi-particles, no. Everything is kind of damped. We're just looking at the electron Green's function. The absence of quasi-particles and spin-ons and all of that appears in the pseudo gap. Then we can talk about such things, but not in the strange metal. Actually, that reminds me of one thing that I didn't mention, which is for the SYK model anyway. How do we know there are no quasi-particles? There isn't some spin-on. The reason we know is, again, because of this. So if you had some quasi-particles, the number of quasi-particle is of order the system size. So, quasi-particle label of a momenta, the number of possible momenta is of order the system size. So, and the energy of each quasi-particle varies with some power of the inverse system size, 1 over the system size or 1 over square root of the system size or something. So if we just count over some small energy interval, how many body states do I have? Well, at low energies is of order n to some power. It's polynomial in the system side. It's not an exponential in the system side. So there's just not enough quasi-particles to give you so many low energy states, no matter what the decomposition you want to make.
Okay, so I think it's thanks Subir again.